The actual motivation for the example that I'm about to give you comes from some work that I'm doing with conformal functions on the complex plane. However, it's too difficult to get into details of that, so I came up with a one-dimensional baby example that still captures the phenomenon that I found initially quite surprising, but later kind of obvious, as it is usually with math. So the example is of a sequence of homeomorphisms that locally uniformly converge to a limit function that is defined everywhere except for one point away from which that local uniform convergence was assumed was happening. And the consequence of not being uniformly convergent on that point is quite the surprise part. It turns out that that one point where we did not have the local uniform convergence has mapped basically to a segment. So the example will be philosophically that the point x equal 1 in my example will be mapped onto the whole segment 1 to 2. I'm going to show you some Desmos pictures illustrating these functions. They're very explicit and easy to make. But here's the thing. Each fn in my blue picture here maps the segment 0, 2 onto the segment 0, 3. So each fn is surjective and covers this whole segment. So the point 1 maps to somewhere, right? Actually, every time under fn, that will map to 2. Like 2 will be fn of each. Fn of 1 will be 2 for each n. But then ultimately, the limit map will all of a sudden not cover anything here. So this part up to 1 will be out of the image of f. In other words, 1 will be mapped to this whole segment, and complement of the point 1, which are these two intervals, will map to this side. So this part will be covered, this segment will be covered, but not the middle under the map f. So what is an example of this? It's very easy to make if you happen to know that x to the n's converge uniformly on 0 to 1 minus epsilon, but never on 0, 1, 1 included in it. So anytime you are before 1, up to before 1, these uniformly converge to 0, to the powers of n, but after, near 1, they don't, and that results actually into discontinuity of this function. So that example everyone has seen in analysis, right? That xn's pointwise converge to 0 everywhere from 0 to 1 excluded, and at 1 they converge pointwise to 1 because each single one has value 1 at x equal 1. So to turn it into a homeomorphism, I just added the constant function x to give it a slope so that it doesn't become horizontal. And therefore, my functions fn's will be this purple or blue, whatever you see, functions graphed here. And once I play with the exponent, I can show you like this is x equal 2, x equal 22, and you get the idea, x equal 52, and so on. So these are exactly mimicking that behavior of xn's converging to 0, so that basically we are left with function y equal x. The tail, the part after x equal 1, is just for illustrative reasons, just for illustration, that I want to continue the homeomorphism. It kind of becomes nicer when, or this fact that the x equal 1 value blows up to a segment becomes more compellingly illustrated if I add that part. So let's fix one value, say at 32. So look at my purple function. It is a homeomorphism. It's a strictly increasing function with a continuous inverse. For every value of n, that will be that. And the their pointwise limit, if you look at any one x, you see that after some number, those values will be killed, except for value of x equal 1. So the limit of these functions will be this red function away from 1, not defined at 1 really. So that is the pointwise limit of my purple graphs. And as you can see, the image of the red skips the whole interval 1 to 2 on the y-axis. You have to look. We can look at it this way, that is not covered, or we can say this function, if the limit of these functions maps the point x equal 1 onto the whole segment from 1 to 2. And there is a way actually in topology to make this statement precise by using notion of quotient spaces. So if we look at the interval 0 to 3 and quotient out this middle segment 1 to 2 into 1 point, so we define this equivalence relation that if 2 points are from the interval 1 to 2, we identify them. Then we can also put the quotient topology on it, and then we can make this statement extremely precise that the limit function f here is a function mapping 0 2 to this 0 to 3 quotiented out space. F, this limit f is still a continuous function, and it is well defined at 1, an image of 1 is the quotient or the class of any 1 point picked from segment 1 to 2. Again, the real motivation for me for such examples was in the plane, but the core idea now is there. So it is possible that a sequence of seemingly very nice homeomorphisms can do extreme things to point on the boundary of the set where this local uniform convergence is happening. Now that I've said this much, let me just draw a picture. So for example, the kind of locally uniformly convergent functions that I'm looking at is, suppose you have a sequence of homeomorphisms defined on C or C hat, if you're looking at Riemann sphere, minus this one compact closed set P. So suppose you have a sequence of homeomorphisms with certain properties, and you wish to subtract, which is very easy in complex analysis to often to subtract locally uniform convergence out of conformal maps. So this F exists, and then you wonder what this function, you wonder about the behavior of this one function. You can also have multiple connected components taken out of C, so let's say P, P1 and P2, things like that. For example, if you have these locally uniformly converging functions to an f, P1 and P2, there is no guarantee that image of this 1 point P1 will actually be 1 point. And that's exactly the kind of phenomenon that happens here. So it could happen that if actually maps this or blows up this P1 into just a whole disk or something even larger. And this is just as possible as it was in the previous example of how this 1 point got blown up into a whole segment. So similar phenomenon happens. So again, this mapping of point to a disk is in the sense of in the quotient spaces. And the reason it's possible is that technically f is not none of the f's or fn's are defined actually on P1, so they are defined on the exterior or away from this point. So they can really just a stretch. Actually, probably my example, if you can radially do it, you can exactly create one such example, right? So my example did it for 1 point on a segment, so just define radial functions. I mean, radially just define the same function. Anyway, so I liked this example, quite surprising, and hopefully you will find some joy in it as well. See you in another video. Thank you.